Section 2.3, functions. A function is a relation such that for every valid input there exists a single possible output. The x values, which are the independent variable, are the elements in the domain, and the dependent variable, which is the y value, are the elements in the range. So the definition of domain and range, definition of domain, set of all valid inputs, and the definition of range is the set of all possible outputs. Function notation is y equals f of x. We say f parentheses x parentheses f of x. So if a relation fits this property, so for a valid input you get a single possible output, we can replace y with f of x and be a little more specific and say this is a function. So some examples we're going to take a look at. We're going to determine if relations are functions, and we're going to do that algebraically and graphically. We're going to find the domain and range. So to determine if this relation is a function, we can isolate y and see if we have that well-defined property. So I'm going to subtract 3x from both sides. And we get y equals 9 minus 3x over 4. If you wanted to write this kind of in slope-intercept form, we could just rearrange that there. And we can replace y with f of x using function notation. This is a function. This is a function because it's well defined, which is for every valid input. So in this case, this is a linear function. The valid inputs are all real numbers. We get a single possible output. There's no way to get two different outputs if we picked an x value. And just for practice, let's compute something like f of 8. So this notation means replace x with 8. So for practice, we're going to compute f of 8, which means replace 8 anywhere there's an x. When we do that, we get negative 15 over 4. That's the y value. And so that tells us that the ordered pair 8 comma negative 15 over 4 is on the graph of f of x. Alright, let's take a look at x squared plus y squared equals 1. If it is, we'll be able to isolate y and rewrite using function notation if it has that well-defined property. Keep in mind when we square a root right there that every real number has a positive and negative root, so we have to put plus or minus out front. And that shows us that this relation is not well defined, which means this is not a function. So for example, if we chose a valid input and plug that into this relation, we'd get plus or minus the y value. In order for a function to fit the definition for a single valid input, there has to be a single possible output. In this case, there's going to be more than one possible output, which means this is not a function. So let's take a look at that on the graph. The graph of this is x squared plus y squared equals 1 is a circle with radius 1. And we can take a look at what's called the vertical line test. So if we chose any x value, if a vertical line is drawn through that x value and it touches the graph more than once, that is not a function. And this is just a visual way to say the same thing that we did above. So it does not pass the vertical line test. That means it is not a function. Let's take a look at these two. So here, I've already written in function notation. Quickly, we're going to be able to see that this is a function. This is a cubic function. So if we took a vertical line and we went from negative infinity to positive infinity, we would never hit the graph more than once. So this passes the vertical line test, therefore it is a function. Now this relation here, we have y squared equals negative x. If we went from negative infinity and took a vertical line across the graph, we would hit the graph more than once. And since it doesn't pass the vertical line test, it is not a function. Let's take a look at the definition of increasing and decreasing and constant. Here's the definitions of increasing, decreasing, and constant. Now, visually looking at the graph, this is pretty easy to determine. The function has to be defined on the interval, and what this says right here is for a smaller x value, the y value is also smaller when you input that. So that's when the function is increasing. And what we're going to be looking at is upward movement from left to right. So we're going to read this graph in terms of the x-axis just like normal, and if the graph is moving upwards on an interval, that means it is increasing. Decreasing, the only thing that's going to change is that the y value for the smaller x value is greater than its next y value. So this means the graph is moving down from left to right. Now, if you look at the difference here for a constant interval, that just means the y values are going to be the same on that interval. So let's take a look at this graph. Now this isn't anything in particular. This is just to identify the intervals. So from negative infinity to positive infinity on the x, here the graph is decreasing and then it changes right there at x equals -2, begins increasing. Now, from the labeling of these ordered pairs, we have -1 on the x, and the next ordered pair right here is x equals 2. The y values don't change. So here we're constant, and then from x equals 2, the graph starts to move down again, so it's decreasing. Looking at the graph, it's pretty easy to see where it's increasing, decreasing, and constant. Let's write using interval notation. So the graph begins increasing at -2 on the x, so parentheses -2, and then it changes from increasing to constant at -1 on the x. Remember, we're writing this in terms of the x-axis. It's that upward-downward movement which tells us increasing or decreasing based on the definition, but we write the interval notation from left to right. If that weren't the case, we'd end up with intervals with a bunch of overlapping y values, and so we're decreasing from -infinity to -2. This is an open interval, so parentheses, and then constant from -1 to 2. Let's get a little bit of practice. Oh wait, we need to find the domain. We were going to do this example number 4, find the domain range. Let's do that real quick. So looking at this, the value -3 causes division by 0. So -3 is not in the domain. Writing that in interval notation, we need to write all real numbers except -3, and that's what this says. It just says this using interval notation. There are no other values that are not valid, meaning every other real number except -3 is a valid input, and we substitute it into this function, we will get a single possible y value. Okay, now if we're going to take a look at the range, for the most part in this section, we're finding range by looking at the graph, but this one is a good example for finding range, and do that algebraically. 1 over x plus 3 cannot equal 0, so 0 being an output. No matter what number we choose for x, that's a valid input. No matter what number we choose, 1 divided by any real number can never be 0. So the range is -infinity to 0, and then we're going to union that 0 to infinity. Every other number is possible. Every other number is a possible output in the range. Okay, let's practice with just some function input output. Let's say f of x equals x squared plus 5x. First one we're going to do is f of 3. And what that means is anywhere there's an x, replace it with a 3. Let's do f of t. So t being an element in the domain, anywhere there was an x in the original, we replace with t. let's do f of x plus h. So when we're changing inputs at x plus h, it still represents an element in the domain. It doesn't matter if we're using different variables, different letters, placeholders, combination of letters and numbers. What this is telling us to do in function notation is anywhere there is an x, replace it with the quantity that's in here. So if you see the original, parentheses, x is the original input, and x shows up there, x shows up there. You take the new input, which is x plus h, and replace it. So when we multiply this out, that's x squared plus 2xh plus h squared. Distribute the 5 across the x plus h, so plus 5x plus 5h. And then none of those are like terms, so we cannot combine any of those terms.